All right, so right triangle trigonometry. First of all, let's make sure that we know what all the trig ratios represent. Okay, most of you can tell me SOHCAHTOA, but then you kind of blank on what it actually means and how you actually use it. So here's a typical right triangle. I have a theta down there in the corner. Theta is just a variable that we use typically when we're talking about angles. We use theta usually instead of x, but we could use x as well. So if theta is our angle right down here, most everybody's good with always identifying the hypotenuse. Okay, that's usually not a huge problem, but sometimes the triangles are a little bit more squished and it's not quite as obvious. I always use the little right angle as an arrow. That corner points directly to the hypotenuse. Oh, that's where the extras are. That corner points directly to the hypotenuse. Now, I like to draw this curve right here at the angle because that curve always touches the hypotenuse and it also touches the adjacent side. So the adjacent side should be the next easiest one to identify. If you are adjacent to something, you are right next to something. So that is the side that is right next to our angle. So like I said, this little curve kind of helps me. It touches the hypotenuse and it touches the adjacent. So then that leaves this other side over here for the opposite side. Okay, and it's always directly across from that theta. So like I said, most everybody can tell me SOHCAHTOA. Let's make sure we know what it means. SOH. Okay, that's the so part. So the S stands for the sine of theta. The O stands for the opposite. The H stands for the hypotenuse. C-A-H. C stands for the cosine of theta. A stands for the adjacent. H stands for the hypotenuse. TOA. T stands for tangent of theta. O is for the opposite. A is for, and I have it wrong up here, that should be the adjacent. I was on the hypotenuse train there and did not type the right thing. Adjacent for the tangent. Okay, opposite over hypotenuse is sine, adjacent over hypotenuse is cosine, opposite over adjacent is the tangent. There are many different phrases that people use to help remember. There's one, some old horse caught another horse taking oats away. So it gives you those letters again. Another one, some old hippie caught another hippie tripping on acid. They always think that was funny. I learned, oh heck, another hour of algebra. So that doesn't include the sine, cosine, tangent parts, but it does the opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent. Whatever it takes for you to remember, just remember sine, opposite over hypotenuse, cosine, adjacent over hypotenuse, tangent, opposite over adjacent. All right, so how do we use this? Let's find some trig ratios. This is number one on your worksheet there. Okay, this is number one on your worksheets. It asks for the sine of theta, and it gives us two sides of this right triangle. So let's identify. I always start by identifying the sides. So 18 is my hypotenuse. 8 square roots of 2 is my adjacent. So that leaves this other side over here as the opposite. Just put a simple O, A, and H. That's all you need to put to let yourself know which sides do I have. Now sine is supposed to be which sides? Opposite over hypotenuse. Do we have the opposite side? No, we don't have the opposite side. We do have the hypotenuse. So that means we need to use the Pythagorean theorem to find our opposite side. So our opposite side plus our adjacent side squared, both of those squared, equals our hypotenuse squared. Now, the only thing that I caution you about with using the Pythagorean theorem, y'all are pretty good at the Pythagorean theorem, is that you must put that 8 square roots of 2 in parentheses before you square it. Because if you just stick a squared on the end of the 8 square roots of 2, all it's going to square is the square root. It's not going to square the 8, and it's supposed to. Okay, and then we take the square root of the answer. So our opposite side is 14. So sine is the opposite over the hypotenuse, 14 over 18. If you can reduce it, then you go ahead and reduce it. So those are both divisible by 2. So it reduces to 7 over 9. That's kind of like what we ran into with that ACT question the other day, where the sides of the triangle, they gave us the two different trig ratios and the sides of the triangles didn't match up. It's because they came from reduced fractions. So if you can reduce it, but the sine of the angle is equal to 7 over 9. The ratio of the opposite side over the hypotenuse is 7 to 9. That's what the trig tells you. Trig tells you a ratio. Okay? We don't know what theta is. We could find theta, and we're going to get to that here in a minute, but right now we're just wanting to know what's the ratio. All right, let's look at number 7. Look at number 7. It gives it to us in words. It says find tangent of theta if cosine of theta is equal to 3 over 5. So we're not given the picture. We're not given a diagram here. So let's just go with what we know based on the information we're given. Cosine is what over what? Adjacent over hypotenuse. So my adjacent side is 3. My hypotenuse is 5. So I'm just going to sketch myself a little right triangle. It doesn't need to be perfect. I'm just going to stick theta right down here. It doesn't matter which place I put it in, just so I put my measurements in the right places. So this is my hypotenuse, this is my adjacent, this is my opposite. So my adjacent is 3, my hypotenuse is 5. Tangent. It wants tangent. Tangent is the opposite over the adjacent. We have the adjacent, we don't know the opposite. We need to use the Pythagorean theorem. So O squared is equal to 16, so O is equal to 4. Now we're actually going to talk about this here in a minute, but this is what we consider, this is one of a special right triangles, okay? 3, 4, 5. If the legs are 3 and 4, then the hypotenuse is 5. So if you know any of those two of those three pieces of information, you can find the third. So in this case, we knew the hypotenuse was 5 and one of the legs was 3, so we should automatically be able to say that the other leg is 4. But Pythagorean theorem still works. It just gets you there a little bit faster if you recognize the special right triangles. All right, back to the trig. Tangent of theta is equal to the opposite. We found out it was 4 over the adjacent, which is 3. So that's the answer to number 7. Questions? Reviewed, right? Hopefully. That may have been a new kind of question, but the trig. Let's look at number 11. Okay, I said that we could find the angle. That's what we're going to do here on number 11. Finding an angle using trig. So number 11, they give us a leg of this right triangle. They give us the hypotenuse of this right triangle, and they ask us for the base angle. So when they're asking you these questions, you need to identify, well, in relation to that angle, which sides do I have? Well, 59 is the hypotenuse, right? That's the easy part. 15, is that the adjacent or is that the opposite? Opposite, okay? So I have the opposite, I have the hypotenuse. Which trig function are we talking about? Sine. So sine of theta is equal to the opposite, the opposite over the hypotenuse. Now, we're trying to solve for theta. To solve for theta, we use the inverse sine. Okay, we need it on the other side. Theta is stuck inside the sine. You don't divide by sine. Sine is not a number. Okay, sine is not a number. It is a function. It tells you for this angle, you put the opposite side over the hypotenuse. So if you're trying to find that angle, you have to use its inverse function to do so. Now, make sure, number 1, that you're in degree mode. Every time you reset your calculator, it puts in radian mode, so make sure you're in degree mode because we want these answers in degrees. And the inverse sine is the second sine. So 15 over 59 So theta is approximately 14.728 degrees. I think on your paper, does it say round to the nearest degree? I heard a yes and I heard a no. So, yeah. Okay. It does say round to the nearest degree, so the answer would be 15 degrees. That would be the closest degree answer. Okay? Questions about what I did in the calculator? No? Okay. All right, let's look at number 19. Okay, let's look at number 19. Solving a right triangle for all sides and angles. Okay, the instructions say solve the triangle. So that means I need to find all the angles and all the sides of this right triangle. What's the easiest thing to find in this triangle right now? The third side, right? Pythagorean theorem, we can find side AC, right? So 8.3 squared plus x squared equals 13 squared. So 13 squared, 3 squared, square root. So that says x is, it's not exactly 10, but it's practically 10. Okay, 10.005, we'll just call it 10. Okay, now we got to solve for the angles as well. So we got to find angle A and angle B. We know angle C, right? It's 90 degrees. So it doesn't matter which one you use. So somebody tell me, would you rather solve for A or B? I heard B first. Okay, so let's solve for angle B. Now, like I said, it doesn't matter which one we do. It does not matter. If you solve for A, you should end up getting the same answers. So if we're solving for B, use the given information as much as possible. Okay, I'm going to try and avoid using the 10, which was something that I solved for just in case I made a mistake in solving for that side. Use what they gave me. So based on what they gave me, 13 is the hypotenuse, 8.3 in relation to angle B, 8.3 is the adjacent. So I was given the adjacent and the hypotenuse, so which trig function am I going to use? Cosine. Cosine is the adjacent and the hypotenuse. So the cosine of, I'm going to put a B right there, okay, because that angle is labeled as angle B. So cosine of B is equal to the adjacent over the hypotenuse. When we're solving for the angle, we use the inverse trig. So the inverse cosine of 8.3 over 13 is going to give me angle B. So that gives me approximately 50.3 degrees. So if that's 50.3, do I have to do trig to find angle A? No, I don't have to. I can, but I don't have to at this point. I can just subtract that from 90 because I already have 90 degrees in one of my angles. So I've only got 180 total. So take 90 away from that, that leaves me with 90. So 90 minus that gives me 39.7 degrees for angle A. Now, I absolutely could have done trig to solve for angle A. Let's just talk through that really quickly. If I was trying to use the given information and I was using angle A, 8.3 is what side in relation to angle A? The opposite. So if I had solved for angle A, I could have done the sine of A is equal to the 8.3 over 13. And that would have given, when I did the inverse sine of that, that would have given me 39.7. Okay? So that's how you handle those kind of problems. Now, let me show you something here. This is on the last page. Okay, this is on the last page. Special right triangles. There are two special right triangles that you need to be familiar with. One of them is a 45, 45, 90. Okay, that refers to the angles. You have two 45-degree angles and a 90-degree angle. what kind of triangle would we call that if we were talking about its sides? Well, it's a right triangle, but that's talking about its angles. We're talking about the sides, so is it equilateral? Is it isosceles? Is it scalene? It's isosceles. If the angles are the same measure, then the sides have the same measure. Okay, if the angles are the same measure, then the sides have the same measure. So it's an isosceles triangle. So the relationship that always exists with a 45, 45, 90 triangle is that the sides across from the 45 degrees are the same, and we call them x. The hypotenuse is always that value times the square root of 2. Now let's think about why that is the case. If we set up the Pythagorean theorem here, the side is x, so x squared plus x squared is equal to, we'll say c squared. We're trying to solve for the hypotenuse. X squared plus x squared, what does that equal to? 2x squared. If I'm solving for c, I need to take the square root. So the square root of 2, the square root of x squared is x. So that's where that comes from. Okay, that's why that relationship is what it is. Now, you don't have to go through that proof of that. I just wanted to show you, well, where does the square root of 2 come from? That's where it comes from. It doesn't matter what the side lengths are. If it is a 45, 45, 90 triangle, that relationship always exists. Okay. So let's use that. Let's look at number 1. We'll get back to the 30, 60, 90 here in a second. Let's look at number 1 there on your worksheet. Only one of the angles is labeled with 45 degrees, but if that's 45 degrees, bless you, then we know that that's 45 degrees, right? It's the only angle we have left if there's 180 total. All right, so this side, they gave us the hypotenuse. The hypotenuse is equal to x times the square root of 2. So if we're solving this for x, we need to divide by the square root of 2, right? We're solving for x. X is being multiplied by the square root of 2, so we divide both sides by the square root of 2. Let's simplify what we've got here. When you are dividing and you've got 2 square roots there, you can divide the numbers that are under the square roots. So 10 divided by 2 is 5. Okay, so all I did was the square root of 10 over the square root of 2. They're both under a square root, so I can divide the 10 over the 2. So that leaves me with the square root of 5 in the numerator, because 10 over 2 is 5, so it stays in the numerator. And that's it. That's as much as we can simplify it. You cannot simplify this 5 with this 5, because the one in the numerator is on the square root. That's the square root of 5. That does not have the same value as just 5. So that's as far as we can take this. So that is our x. That is the side across from the 45. So in this case, both x and y are equal to 8 square roots of 5 over 5. You could check it. If you're a little worried about that square root and stuff, type in 8 square roots of 5 divided by 5 times, we multiply that by the square root of 2 to get our hypotenuse. So let's see if that does equal what they have the hypotenuse labeled as. 8 square roots of 10 over 5. They have the same decimal value. Okay, so I was just checking it. Once I solve for the leg, I know that the leg times the square root of 2 equals the hypotenuse. So I was just confirming that my calculations were correct. Okay. Now, the 30, 60, 90 has a little bit more detail because we don't have 2 angles that are the same. So all of our sides have different lengths. So here's what happens in the 30, 60, 90. The side across from 30 is x. The side across from 60 is x square roots of 3. And the side across from the hypotenuse is 2 times the x. Now, I could show you how it's true the same way that I did the other one, but I'm just going to let you take my word for it. Let's look at a problem. Okay. Let's look at number 10. Number 10. So they have the 30 degrees labeled. I'm going to label the 60-degree angle as well particularly because that is across from the side length that they give us. It is across from the side length that they give us. So I have 8 across from the 60 degrees. Well, across from the 60 degrees, that is supposed to be equal to x square root of 3. So we set it equal to x square root of 3. To solve this for x, we divide by the square root of 3. So we have 8 over the square root of 3 is equal to x. Now, we don't leave square roots in the denominator. We do not leave square roots in the denominator, so we have to rationalize. So we multiply top and bottom by the square root that was in the denominator. We multiply top and bottom by the square root of 3. So in the top, you can't multiply things that are under a square root and things that aren't under a square root. So we just leave that as 8 times the square root of 3. In the bottom, you can multiply square roots by square roots. So 3 times 3 is 9. The square root of 9 is 3. You multiply what's under the square root. 3 times 3 is 9. It's under the square root, so the square root of 9 is 3. So that is our value of x. Well, the side across from 30 is our x. So the side across from 30 is 8 square roots of 3 over 3. So y is 8 square roots of 3 over 3. The hypotenuse is 2 times that x. So when we multiply that by 2 times 8 square roots of 3 over 3, that gives us 16 square roots of 3 over 3 for the hypotenuse length. Now, if you were going to try and check this by plugging into the Pythagorean theorem, just make sure that you put the entire expression in parentheses. So this is what I'm talking about. If I'm trying to square this side right here, I got to do parentheses, 8 square root of 3. It had its own parentheses, so I got to close that, over 3. Close my parentheses around the whole expression, squared, plus 8 squared. And that should be equal to my hypotenuse, 16 square roots of 3, over 3. Now I close them squared. Okay, I get the same numbers. So notice how I put parentheses around that entire side length. Okay, I put parentheses around the entire side length. You have to close your parentheses at the end of the square root. That's one way you can kind of check what you did. Use the Pythagorean theorem. All right, last thing I told you I was going to mention the other special right triangles. This has to do with the side lengths. It has nothing to do with angles. It has nothing to do with angles. These are just side lengths. So one type is the 3, 4, 5. Another one is the 5, 12, 13. 3, 4, 5, and 5, 12, 13. So we can use multiples of those numbers as well. Okay, so I've got an example here at the bottom. I have a side, or I have a leg of 9. I have a hypotenuse of 15. 3 times 3 is 9. 5 times 3 is 15. So that means this side is going to be 4 times 3. This missing side is 12. Again, you can use the Pythagorean theorem. This is just going to save you a lot of time if you recognize the special right triangle. Okay, let's look at a 5, 12, 13. Okay, 10 is 5 times 2. 24 is 12 times 2, so the hypotenuse is going to be 13 times 2. The hypotenuse here is going to be 26.